Welcome to our second Hackathon preparation series workshop. A little bit about us for SF Hacks. We are San Francisco's largest collegiate hackathon. We will actually be hosting our hackathon in March of 2022. It will be hybrid, and so to keep updated on anything, we will be posting our links in the chat so that you have more information about our upcoming hackathon. And then until then, we're giving our attendees the opportunity to utilize any sort of workshop or anything that presenters come in to present for our hackathon so that they can use it for our projects. And then I will pass it on to Dr. Puder. I will stop screen sharing.
Well, thanks, Naya, for the introductions, and welcome to you for joining this session. I'm happy to support SF Hacks, and I hope I can give maybe some of you some inspiration on projects you may want to do for the actual SF Hack session. I am not an expert on IoT, I have to be honest. I'm more of a pure computer scientist, but I do have a minor in electrical engineering. Now, that is like a long time ago, and I never quite used that in my profession. But I recently got interested again. So I started equipping my house with all kinds of little toys and gizmos, and that also basically got me back to my beginnings. So I started out as a college student also having to take some electronics courses. So a few years ago, I was asked to hold a two full day workshop on IoT, and I prepared some teaching materials, and obviously, I cannot squeeze 2 days into just one short hour here. But what I want to do is I want to paste a link to this GitHub repository. So I'm an open source guy, so I do everything out in the open. And if there's one thing you want to bookmark, it probably is this GitHub repository. So I'm going to be using the slides and some of the code samples that I have on this GitHub repository. So this contains everything you need to replicate what I'm going to show you here. So it also has the slides and also the Arduino code. But before I go into those slides on this GitHub repository, I wanted to start with some other slides. And let me screen share just some intro slides, and also maybe to date me in terms of my age. So what you see on this page here on this slide is my first computer, the Tandy Radio Shack TRS-80 Model 3. So that was released in 1980 by the Tandy Radio Shack Corporation, a company that has gone defunct by now. They have actually gone bankrupt at some point. There used to be a lot of Radio Shack stores out there, and they're all gone by now. But at some point, they were pretty famous for releasing one of the first personal computers, and this was my first computers. And I wrote down some stats. It was like an 8-bit machine. It had a CPU, a Zilog 80 Z80 CPU, whooping 1.7 megahertz with 48 kilobytes of RAM. I mean, most pictures on the internet, when you browse to any given web page you go to, probably the image requires more space than this whole machine had RAM. But it was great for tinkering. That is how I, in a very playful way, learned computer science before even it was offered in my high school in Germany. When I went to high school, it wasn't even offered computer science. Now, when I compare that to how my nephews grow up, they grow up with these iDevices. I call them iDevices, and I little bit cynically say they are tinker resistant. You know, these iDevices are meant for consumption. They want you to spend money on them, but they're not meant for tinkering. So my nephews don't have that same access to technology that I had. You know, I could open this TRS-80 with a screwdriver and meddle with it. I mean, these iDevices, they are glued together. You can't even like open them to do any tinkering. So fast forward many years or even decades, and there was a professor in northern Italy who created a platform that has become known as Arduino. And the Arduino is basically bringing back this tinkering to people. So it allows you to just be creative and do your ideas, whatever you have in mind. So it's a small a board. I can actually should have pulled out one of my things earlier. I'll hold up one later. So the Arduino now brings this tinkering back to the people, and it's a wonderful, wonderful platform. If you Google nowadays, you will find hundreds, if not thousands, of web pages that have some tutorials and little sketches. They're called sketches, the programs, and guidelines on how to develop different gizmos. I'll show you at the end of my presentation a few things that I'm working on right now. But basically, for today's session, I want to focus on the Arduino. If you can spare a little bit of money, then you can buy a so-called Arduino starter kit. And my slides on the GitHub link that I posted earlier has a link to the starter kit that I've used for my 2-day tutorial. But if you go to Amazon and just search for Arduino starter kit, you will also get at least a dozen different, 1-2 dozen different starter kits. And there's no right or wrong. They all typically have the Arduino as the core component, and then excuse me, here's the Arduino, and then have a lot of the components. They have wires, they have resistors, they have LEDs, they have breadboards. So you can then just pick up one of these starter kits, and they go as low as $20. So if your budget allows that, then I would definitely encourage you to invest in an Arduino starter kit if that interests you. But later I will also show you there's actually an online platform that allows you to do all the basic stuff online, which is great for starting out and just to play a little bit. But I have to say, there's nothing more important than this visceral sense on, having a breadboard and plugging in the cables and seeing something actually flash up little lights. So if you can spare $20, then and if you're interested in this topic, I would definitely encourage you to invest that. So these slides here are not on the on the GitHub slides. So I'm going to switch now to the GitHub slides. And it was just like a little intro, just also to give you a little bit of a background on myself and even dating myself. So I've used the computers in the early 80s, you can make an educated guess on my age. I did want to say a few things. I mean, I have some slides. Again, like this is like the slides here is for a two full day workshop. And obviously I can only cover parts of it, and there is I have a slide here on just the definition of Internet of Things. I don't want to I just want to skip over this. Actually, this term already was coined back in 1999. So it basically, when you think about it, there's also this term what you often hear in that goes along with this ubiquitous computing. When you think about when you use a laptop, when you use a desktop, you consciously use your computer, right? You have a keyboard in front of you, you have a mouse in front of you, and you interact with the computer. So the idea of ubiquitous computing that then led into Internet of Things is that now computers are more in the background. Computers help you behind the scenes. You have sensors that can regulate the temperature of your heating. You have these smart speakers that can react to voice commands. You can clap in your hands and something happens, the light goes on. So that is basically where computer science is pushed behind the scenes. So a lot of what Internet of Things is about is this vision of ubiquitous computing, basically putting the computer behind the scenes but make it useful for regular people. Now, there are a lot of different platforms, and let me I already mentioned the Arduino. What you often also hear in this IoT space is Raspberry Pi. And I wanted to spend like a quick minute on the difference between Raspberry Pi and Arduino. So you can also then shine with your friends, and you can speak you can explain to people what the difference is between a Raspberry Pi and an Arduino. So the main difference is that a Raspberry Pi would be in the category of a mini computer. It's actually a full-fledged computer. And you have connectors where you can plug in HDMI displays. You have USB where you can plug in USB keyboard. It's a mini computer. You can actually run Linux on it. It runs an operating system. So it has an SD card slot where you can put in an Ubuntu image, for example, or different operating systems. And you can then boot this up. Now, they also have what is called, did I mention this here on the slide here? Well, what I will talk about later, GPIO, general purpose input-output pins. And you can see this here on the Raspberry Pi on the top left corner. That is basically the starting point where you can connect different peripherals to this Raspberry Pi. But one important thing is that a Raspberry Pi is a mini computer. It runs an operating system. So everything you can do on the Linux, you can do on a Raspberry Pi. It's low powered, so it has less processing power than your desktop. So it's not really a good gaming platform, obviously. But it has these GPIO pins here in the top left. And actually, can you see my mouse when I hover my mouse over here? So, okay, it's good. It's good for me to know if I can point to things on with the mouse. And also pretty low price, $25 for like a mini computer. That's not too shabby. If you want to have a little Linux environment and you want to tinker with it, that's definitely also a good thing. But take a look at the some of the data here. So you have a lot more RAM, and actually this 250 megabyte is on the lower end. So there are newer versions of the Raspberry Pi that even go up to 4 gigabyte of RAM here, not just the 1 gigabyte RAM I show here. The Arduino on the other side, and that is one thing that people sometimes have a hard time wrapping their head around. The Arduino is in the category of a so-called microcontroller. And one of the major differences is that it does not run an operating system. These microcontrollers are so small and so restricted in their processing power that you cannot run an operating system. And if you just look at the data here, they have like 2 kilobytes of RAM. That's even less than my old TRS-80, right? So, which had at least 48 kilobytes of RAM. But they do run at 16 megahertz, so at least a little bit faster than my old machine. But they also have these GPIO pins here, these general purpose input-output pins, and you can actually see them here on these pin headers here on the left and on the right. And that is where you can then connect sensors, and I will show you later how to do that. A benefit of them, one big advantage of them is their power consumption. So they have, if you make use of some low power modes, you can run 4 years on the 9-volt batteries. That also gives you the chance of building something in a little box and put it in a corner of your room, and you don't necessarily need a power outlet. If you take a 9-volt battery and you run it with a Raspberry Pi, 4 hours and the battery is dead. The Raspberry Pi is pretty power hungry. But here you can see that the one benefit of the Arduino is that it is if you have to do some special work to run it in low power mode, but if you do it right, you can easily run an Arduino 4 years on a 9-volt battery. Now you may ask yourself, okay, now you're used to running writing code in Java, in Python, in JavaScript. The Raspberry Pi supports all these programming languages, and you have compilers like GCC or LLVM to compile your C++ code on. So it's exactly like on a desktop. Now, if you don't have an operating system, how does this work then on the Arduino? Well, the good news is you can still use C and C++. So, and I will show you later, then it's a limited version of C++, so it's not the full-fledged version that you have on the desktop, but it's powerful enough to write some pretty sophisticated programs that run then on this tiny microcontroller. There are some other embedded systems, and I've become a big fan of the expressive lines of microcontrollers. So there's it's a China-based company. They produce these ESP-based microcontrollers. The 8266 is actually, they discontinued this one. There's a new version, the ESP32. I should probably also update my slides here. So this were like 4 years ago. This was hip. But I mean, just look at those numbers here. I mean, even this old microcontroller, that's already pretty impressive here. Running at 8 megahertz, having a 32-bit Transillus core. It has 46 kilobytes for RAM, 96 kilobytes for data. It has a built-in Wi-Fi adapter, and it also has built-in Bluetooth. It also has these GPIO pins and other connectors. It is super small. So this picture here is just the size of a quarter. So if you take a coin a quarter, this is about the size of this thing here. And it also is pretty low in power consumption, at least as long as you don't use Wi-Fi. And this cost like $1.70, this little tiny guy here. So also extremely cheap for what it gives you in terms of power. Anyway, so it's just kind of like a very high-level introduction to the platform. Now, for the rest of this tutorial, I'm going to focus on the Arduino, and I will show you. My goal is to get you up to speed on a hello world for the Arduino, and then just at the end give you maybe some thoughts on what you can do, maybe, and hopefully inspire you to do your own things for the Arduino. Now, I do want to quickly go through some basics of some electronics stuff. And you probably have heard some of those terms, but I want to be a little bit more formal about it. Now, again, with a word of caution, I'm just running through some slides here. At SF State, we have the School of Engineering. They actually have 2 programs. They have computer engineering and electrical engineering, and you can take many classes that deep dive on everything I'm going to talk to here. So I'll just give you basically it's like a very high level overview on maybe some things that would be good to know in order to avoid some issues later. And Kevin, as last time, please hit me over the head if I'm saying something wrong here, since I'm not the my electronics courses were a long time ago. The first slide here I want to show is the difference between current and voltage. So, you know, I mean, you all know that to do anything with any electronic device, be it a vacuum cleaner, be it a microwave, you plug it into a power outlet, right? A wall outlet. So any electronic device depends on movement of electrons. So by plugging it into the wall outlet, you have these electrons that move through the circuit, and that then allows the circuit to these devices to actually operate. Now, there are 2 important concepts. One is called the current, which is basically a measure of the amount of electrons moving through the circuit. And the unit that you use to measure this is called ampere or amps. So that is the unit that describes the current flowing through the electrons flowing through a circuit. Then the difference between the power potential, basically the number of the free electrons between 2 points, is called the electromotive force. And the unit to measure this is called voltage. So, so volt and ampere, that may have come across, you know, you probably all know at least that here in the US, you have like 110 volts coming out of a wall outlet, right? I mean, that is the unit that describes the voltage coming out of the wall here in the US. I'm German. In Germany, I can tell it's actually 220 volts, so it's twice as much, you know. So then, here in the US, One thing that helps to explain this is a plumbing analogy, and maybe experts in electronics would cringe at this, but I find this helpful. So if you just use a plumbing analogy, voltage is equivalent to the water pressure. If you think of like a water pipe, and current is equivalent to the flow rate, right? And these are independent of one another. So there's some correlation, but if you have, for example, a big pipe, you can have lots of water flowing through, but there may not be a lot of water pressure. But even for a small pipe, if a fire truck is holding their hose towards you, it still manages to push you over. So that would then be the water pressure here. So, but there's not that much water coming out if you compare it to a river, right? A wide river. So I think this plumbing analogy is actually helpful to explain on a very high level, these difference between voltage and current. In electronics, it's common to explain this or to have schematic, so-called schematic symbols. So you will see this later when I explain some electronic circuits. So here you see the schematics for a battery. And the battery is for example, like this 9-volt battery, you have a positive and a negative terminal. And in the schematics, you then typically have like a little plus, little minus. Sometimes they also have like this heavier bar and a not so heavy bar to denote between plus and minus. And then often you see then these arrows showing, well, so here I have a battery, 5 volts. So the arrow is going from the positive to the negative terminal. So to highlight this difference in potential between 2 points. And then here you have the arrow along the line to denote then the flow of the current of the electrons. So this battery here, this block battery is very common. It's actually a 9-volt battery. So that is pretty common for if you go to any store and buy batteries. The Arduino is powered with 5 volts. So if you just connected the battery to an Arduino without any provisions, then you would fry the Arduino. So you have to also be a little bit be careful. Obviously, you don't want to put in more voltage than the device can handle. So when you talk about an electric circuit, so here's like a nice example. So here's another schematic. The circle with this X through it is schematics for a light bulb or like a little, something that can emit light. And when you want to have a circuit operate, you need to have a closed circuit, right? Imagine if you have your water pipe, but you cut it off, you close the valve, then water cannot flow and you cannot operate your circuit. So here on the left, you can see it's actually an open circuit, right? Because the electrons, they cannot flow through the circuit, so the light bulb cannot go off. On the right side, you can see there is a closed circuit, and you can see the electrons can go from the negative terminal through the light bulb to the positive terminal, and that is where the light bulb would light up. So there's also why, like if you look at your wall outlet, I mean, you all know that you have actually 2 pins that go into it, not just 1 pin, but 2 pins. That is because you need to have a closed circuit, otherwise electrons cannot flow and you cannot power your electrical device. So the next thing I want to talk about is resistance. So again, going back to my piping analogy, imagine if you have a pipe and you pinch it, like you have like a water hose, and then if you water your garden, but then you pinch maybe somewhere the pipe. Well, by pinching it off, you reduce the flow, the water flow, right? I mean that you added a resistance to the water flow. Well, there is also a way to do that in an electrical circuit. There are some materials that are called conductors, which actually are this is material where electrons can move freely. So examples would be copper, silver, gold, aluminum. These are all conductors, meaning that they are good for letting electrons flow. Then there are other material called insulators, which basically do not let electrons flow at all. So, for example, would be glass, paper, and rubber. And actually, when you think about it, when you plug in, for example, your vacuum cleaner or your microwave into a power outlet, you know you have a cable. The cable is wrapped in plastic. And why do they do that? Well, the plastic acts as an insulator to protect you, the human, with the wires that are inside the cable. So here you have an example of any cable for any of your electronic device has the insulator, the plastic wrap around the cable to protect you not to electrocute yourself. And inside the cable, you have then a conductor that allows then to let the electrons move freely. Now, there are some materials that don't belong in either category. So there are basically materials that are not good conductors, but also not full-fledged insulators. Carbon would be an example. Carbon is a material that is neither an insulator nor it's a conductor, but it is an example of a material that would then provide resistance to electrons. And there's also a unit called ohm, named after a long dead person called George Ohm. Kevin, the guy's name is George, right? Who was what's the first name of the gentleman? Do you remember?
I don't remember.
Yeah, okay. Anyways, last name Ohm. You often see then this omega symbol to denote the ohm. But basically, ohm is the unit for resistance. Now, the very first thing, if you take any electronics class, is then something called Ohm's Law. And it's basically a law or an equation that puts the voltage, current, and resistance in one simple equation. And you see it right here. So current basically is voltage over resistance. And when you think about it, if you just think about it here, what this means here. So let's just say if you increase the resistance, right? You increase the resistance in your circuit. Well, then you make it harder for the electrons to flow, right? Obviously, then the ampere, the flow of currents will then go down. So the more you increase the resistance, the smaller will the I will get here, right? Because if you have this fraction here, the bigger the denominator is, the smaller the number gets. Likewise, if you increase the voltage, then obviously then you increase the current again. So then if you increase the voltage here, then the ampere goes up. So I think it intuitively makes sense if you go back to the plumbing analogy. And here on the right, I have the electronic, the schematic symbol that you often see in electronic circuits. It's a wavy line. Sometimes you also just see like a little box that denotes a resistor. But basically, in schematics, you see R for resistor, and then U for voltage, and I for current. So by the way, I'm totally okay if you ask questions. Don't wait for me to ask if there are any questions. So feel free to just interrupt me if there should be any questions. So as one quick example of Ohm's law, so here is then a complete circuit. I have a battery symbol here in my schematics. I have a resistor now, not a light bulb, but just a plain resistor. And it's a closed circuit. So here electrons will flow. So let's just, as for the sake of the example, let's just say we have 5 volts and we have a resistor of 100 ohms. So we want to know what is the current? Well, we just simply use Ohm's law to just plug in the numbers. So 5 volts over 100 ohms is then 0.05 ampere, or if you then convert it to a different unit than milliamps. So if you had a circuit like this with a 5-volt battery and a 100 ohm resistor, then you would measure a current of 50 milliamps. So that is my little crash course in electronics. I mentioned this because there is one thing I will mention in a few slides down the road here, but that is why I mentioned the Ohm's law here. Let me talk about the first specific component here, and that would be an LED. And LED stands for light emitting diode, and is a favorite beginner's toy to play with. Already invented in 1927, so it's been around for a long time. Now there are a few things in there in this acronym LED. So light emitting, well, it emits light. So if you light it up, it actually then lights up. But there's another letter in here, the D, the diode. And the diode basically means it's a valve, meaning that it allows current only to flow in one direction. And let me hold up a diode here in the camera. So this would then be an actual LED. And if you buy one of these starter kits, that's what you would get. Now, if you look at the slide here, you can see that these two wires have different length. And if I hold up the LED, you can just maybe, if I hold it up in the camera, you can actually see that those two wires, and maybe let me use a different background. You can probably better see if I do it like this, or maybe not. You can maybe just barely see that those two wires are also different length. And that is because there's these two terminals are called anode and cathode. And if you want to play with an LED, which is the first thing we will do here in this tutorial, is that you have to keep that in mind, because a diode again means that current is only allowed to flow in one direction, meaning it's important the orientation in which you plug in this diode here. If you plug it in the wrong way, it will not light up. So LEDs come in different shapes and forms, and I will show this later here. So here is an example of so-called, and my index finger here, this one here is called a 7-segment display. It's basically you have 7 LEDs shaped in little bars, but by lighting up these bars in different patterns, you can render digits from 0 through 9, and I will show you this later. And they're also used for infrared LEDs in remote controls. So actually, if you were to crack open your TV remote, you would also find an LED, but it would have like a clear tip here, but it emits ultraviolet, it emits infrared light, and that is used in remote controls, which is also when you point your remote control the wrong direction, the light, infrared light, cannot go to your TV remote and nothing happens. So the reason I made you listen through my little Ohm's law and current and voltage explanation is because when you first want to play with an LED here, and this, by the way, is a schematic for the LED, I had it on the previous slide. I mentioned earlier that the Arduino is powered by 5 volts. So you need to, if you were to connect the LED with 5 volts, it would just go boom. It would literally destroy the LED. You need to put a resistor in your circuit in order to then reduce the current to protect the LED from being physically destroyed. And you can use Ohm's law to compute how much resistance should you have. And I will not walk you through here the math here. It's very, very simple. You have to look up data sheets. You have to look up how much current and voltage can the LED take, and you have to then compute basically the resistance. So a very common resistance for making use of an LED with 5 volts is 220 ohms. There's also, when you buy these starter kits, you will see they have like 20 of these, like they have a lot of these 220 ohm resistors. Why? Because, well, this is a very common resistor if you want to do anything with LEDs. So let me talk about then how can you do some prototyping. And one of the first things that you will quickly then see also if you buy these starter kits is so-called breadboards. And I have a breadboard here. Actually, I already have something plugged in here. You can see here's an ESP, here's an FPGA. So I basically just plug them in. But let me, I think I have a box here somewhere. So here is like a breadboard that doesn't do anything, but the point is, let me find a cable here. So what is difficult to see in the video is that they oh, come on. So there are like a lot of little holes here on this breadboard. But the idea is that you can plug in a wire. So you can see that I just plugged in a wire, and I can make connections now between different holes. And one thing that is important, and that is why I also put it up here on the slide, is you have to understand how these little holes are connected. And if you take a closer look again at a real breadboard, you can see on the top and the bottom, there are like 2 rows. And then here there are different columns. And that is then what you can see on the slide, except I rotated it by 90 degrees here. So you can see here are on the sides, there are 2, well, in this flipped orientation, it's now 2 columns on the left and the right, which are typically used for power rails. So you can also see blue and red for plus and minus. And then in the center, you can see then these holes, and you can see the color here. The green indicates so every row, these holes are connected. So basically, if I go back to my breadboard here, so if I use the topmost row, it doesn't matter if I plug it in, let's say the top left here or the next one to it. It doesn't matter. Any one of these holes are connected. So this is all like they're all like connected. It's also how you can then make connections. How you can then take the second cable and plug it into the same row. So now you have these 2 cables, because they are in the same horizontal row. These would actually then be electrically connected. Okay, so that's how then we build up circuits later on. So the first circuit that I do in my tutorial is basically Hello World electronics. And you can see the schematics here, how to build this up. Now, this Hello World electronics, we are not yet writing any code. I am just using the Arduino as a fancy power supply, okay? So if you take a closer look at the Arduino, and this might be harder to see here, but you can see those pin headers here on the bottom, and you can see a blue and a black cable coming out. This is basically then also 5 volts. So the Arduino, this development board, also then gives you 5-volt power supply. So this circuit here is just the Hello World electronics. We don't have to write any code. I'm just using the Arduino as a power supply to light up an LED. Now remember, the Arduino is powered with 5 volts. We have to create a closed circuit, and we have to protect the LED with a resistor. Otherwise, it would be you would fry the LED. Now, where is the closed circuit here? And let me just trace with the mouse from the ground terminal. to the positive 5 volt terminal. So let me take a look at my mouse here. So I'm starting out here with the ground on the Arduino. There's a cable, black wire going down to this, now for in this orientation, the vertical row. So basically all these holes here on this topmost row, they are all connected. So the electrons, they go from negative terminal down here to the breadboard. They can move over here along horizontally. They can go to this wire here that goes down here. Now to this hole over here, and now here, these terminals are connected. So the electrons can continue to flow down here into the resistor. The resistor connects then to another vertical column. It goes up into the LED, through the LED to the parallel column, down to the wire. At a little corner, there's like a right angle corner to then the bottom row, and then up the wire here to positive 5 volts. So here I have a closed circuit, and I basically now, if you were to do this on a real Arduino, then if you were to build up this circuit, then the LED would light up. Now, you don't have an Arduino at your house right now, so let's have some fun, because there is luckily an online platform that has done an excellent job on providing a simulation environment where you can do already a lot for this tinkering in your web browser. And this website is called TinkerCAD. And let me just post the link into chat. Wait, where am I? Zoom. So I'm just pasting a link into chat. So you can bookmark this or you can just open a tab and look at it later. But what I'm going to do now is I'm going to do a live walkthrough here. So I already logged into this website here, and so it will look something like this. And you can do different things here, but I want to do, like here on the left, I want to create a circuit. And then there's a big button here, say create new circuit. Let me click on this one. So on the right, you see now all the various components that they can simulate. And there's not a whole lot, but it's enough. And so, for example, you can see they have like an Arduino here as a point and click component. So I can just click on it, and I can just move it over here to this canvas. Here's a breadboard. I can move that over here. And then I can add an LED. So let me put an LED here. And okay, I forgot now to do wires. I think it's just point and click. Actually, you can see here on the bottom rail of the Arduino, you can see like the various pin headers here. And actually you can see here, this one, 5 volts. Okay, so let me just, like I did in my example, and I think you can just simply drag this over here, and you can drag it to any of these holes. So let me just maybe do it like I did in my tutorial here. So I think I also can go in corners. So let me just click with a plus 5 volts, and then here ground, since we always need this closed circuit. So I also then go from ground. Let me just do it a little bit nice and go to the negative rail here. And let me just first do the LED without a resistor. Okay, let me do like the simulation of a catastrophe. So I'm going to connect then the one side of the LED with the ground rail, and then the other side with the positive rail. So notice I've now a closed circuit, right? I've gone from ground. So if I had to trace with my mouse the way the electrons go, here, over here, up here, LED, down, the bottom row, over here, here, and then back to my Arduino. So let's simulate this, and there is a button here called Start Simulation. So let me just click on this one here. And what you can see is here, I don't know if you can see, well, it's LED, but it has a little like symbol saying current through LED is 483 milliamps, while absolute maximum is 20 milliamps. So I've just successfully, in the virtual world, in the metaverse of Facebook here, blown the LED. Okay, so obviously what I'm missing here is I should have added a resistor. So let me do this. So let me stop the simulation. Actually, they're doing a nice job here. You can see, like, this is the USB cable. So because I stopped the simulation, let me click on the start simulation again. You can see how they, and also in this thing, they plug in the USB cable here. So pay attention to the USB cable as I click on start simulation. It's really like a very nice touch here, right? So now you have the power, and now you blow the LED. So let me stop simulation. So let me add a resistor, and I do this. Let me just remove this cable here. I select it, I hit delete, and let me take a resistor, and let me put it here, and I can now drag the terminal down to. So now I have basically added a resistor to my circuit here. And you can click on the resistor, and it asks you for how much ohm, like how much resistance. And remember, to the slide, I said 220 ohms. So let me change the units from kilo ohms to ohms and change it to 220. Okay. Now let me start the simulation again. And you see, we just lighted up the LED without destroying it. Yoo-hoo. So this is your Hello World electronics, right? Just as a reminder, we're only using the Arduino at this point as a fancy battery. I'm only using the 5 volts connector here to light up the LED. I am not running any code on the Arduino. That comes next. So it is just to set the stage. So let me stop the simulation. Actually, before I go there, let me just add one more component. Let me see. Yeah, so here's a push button. So a push button can also be put on this breadboard. Now notice that I placed the push button at the center of the breadboard here. There's a reason for that, because you can see there's like a divider here. It's like a moat, you know, it's kind of like it's separating the columns from the top, from the columns to the bottom here. And this is necessary for the button. Now the button here is just like on off. It's just like your light switch. But let me change the circuit now to to make use of the button. And let me delete this cable here. And let me just include the circuit for the button. And actually, I think I have to go from here. So this is a little bit ugly now. Oh, crap. From here to here. It looks a little bit ugly. I apologize for that. I should have prepped it a little bit better. Let me start a simulation. Oh, then I guess I was wrong. Let me let me delete this cable here. So the button has 4 connectors here, and I've forgotten which ones actually are the ones that go with the button. Let me connect this here. Start simulation. Okay, so now it's not, if I push the button, you can see when I push down my mouse, I push the button. That is only then when the LED is flowing. So let me just trace how the electrons would flow here again. So you go from ground over here to this bottom rail, then here to the wire up input to the button. But if the button is not pressed, electrons cannot flow. When the button is pressed, electrons can continue to flow to this neighboring column here, down here, with the wire over here, resistor, LED, back to positive. So again, I'm not running any code on the Arduino. I just added a button to the circuit, and when I click the button, then the LED lights up. Okay, let me go back to my slides. And yeah, so here's then the push button example, and you can see basically the same thing here. Again, the slides on my GitHub repository have, you can just revisit this and redo this at your own leisure. Now, the next thing I want to talk about that is kind of important is this GPIO that I mentioned earlier, this general purpose input-output. And these are generic pins that both the Raspberry Pi and the Arduino have for connecting sensors and actuators to your Arduino. And they can be configured to either as input or output. And that is then great, because then you can write code to either read the state of an input pin, or you can write to it to control an output device that you connect to your Arduino. The Arduino has 14 digital GPIO pins that you can control individually. And what I want to do now for the next step is to basically show you an example of how to make use of these GPIO pins in connecting a button and an LED. Now take a look at the wiring here. And you have to pay close attention to what I'm doing now here. So first of all, here's a breadboard, here's the Arduino. Notice that, and it might be a little bit small. Again, if you look at the slides, then it might be a little bit bigger. Maybe let me see if I can go into presentation mode. Where is, okay. Okay, now go into slideshow. Do you still see my slides? Okay.
Yes, we see the slides.
Okay, move over here. So it's a little bit bigger. So you can see now here what I do is I connect the ground terminal of the Arduino with the top row of the breadboard. And then actually you can see here it branches out. Then here I have a wire that goes from the top row to the input of the button to one terminal, and then the other side of the button, if you follow the blue cable here, it goes up to the which pin is this? Pin number 2. So you can see then this blue wire is one wire, so connecting the other side of the button with the GPIO pin number 2 of the Arduino. Now, if you look at the other side, I have then here again from ground wire going to LED, other side LED resistor to protect it, and then the brown cable goes into GPIO pin number 6 of the Arduino. So what I'm doing here is I basically connect the button to GPIO pin number 2 of the Arduino, and I connect the LED to GPIO pin number 6 of the Arduino. So now this is the wiring that you have to do on the hardware side. So now I want to show you what you have to do on the software side. If you were to build this up, if you were to build this in TinkerCAD, and I can do this later than when I switch to TinkerCAD again. And if you connect the Arduino to power, nothing would happen. So nothing would light up. So what is missing is some code that you have to run on the Arduino. And let me go to the next slide.
Dr. Puder, I also just want to let you know that the workshop is a little overtime, which is okay. That means we should definitely do a part 2 to get this done. But would it be possible to maybe finish within the next few minutes, like the next 4 minutes, so we can finish up at 6:10?
Okay. Well, okay. You're putting pressure on me now to finish.
I'm so sorry, Dr. Puder.
Yeah.
We will definitely do a part 2, so that way we can showcase all of this even more.
So okay. Then you know, if I okay, how can I do this quickly now? On the Arduino, the code that you write are called sketches. And one important thing to know is that sketches are written in C and C++. So you can put all of your C programming language skills into writing sketches. But there are some differences here. What is the entry point of a C++ program or a C program? Well, it's a function with the name of main. Right? And this main function does not exist on the Arduino. Rather, you have two functions that you have to implement. One is called setup, and the other one is called loop. And what the Arduino does, when you power on the Arduino, the Arduino will call setup once, and then will continuously call loop. So basically, if you plot a timeline down here, setup is called once, and then the Arduino constantly calls loop. And here is an example of a very simple hello world code for the Arduino. And again, this is on the slide, and you can just copy this into the Arduino IDE, or you can use TinkerCAD. And this here, what you see on the slide, is a complete code example. There's nothing missing. There's not something missing here. This is the complete code you can do for an Arduino Hello World. And you can already see that this follows the C++ code here. So const int and pin underscore LED is basically a constant of type int, initialized to 6. And then you have pin underscore button, another variable, const int initialized to 2, and you can already see why this is like 6 and 2, right? Remember that I connected the LED to GPIO pin 6 and the button to pin number 2. But then what I do here is pin mode is a helper function from the Arduino where you configure the pin number 6 to output, and you configure the pin number 2 as input. Just ignore this pull up here. So what you basically do is here you configure then pin number 2 as input. More interesting is then this loop function here. And you can see that here I have another built-in function, digital read pin button, where basically I'm reading the, where I read from GPIO pin number 2, and I put it into a Boolean variable called press. And then here I have another helper function, digital write. I write to pin number 6, which is pin LED, and take a closer look at the second argument of this function here. Does anyone happen to know how this is called in Java and C, C++, like this press question mark colon? It actually has a name in those programming languages.
Oh, is it ternary operator?
Absolutely correct. So it pressed is a Boolean expression, and based whether it's evaluates to true or false, this ternary expression is returning either high or low. And basically what happens here is if you push the button down, then you write high to the LED pin or low if you don't push the button. So what this will do is then, if you push the button down, the LED will light up. And if you let go of the button, then the LED will go off. So that is like a super simple example here. And you can actually make this run in TinkerCAD. And since I am asked to quickly wrap up, I do want to just show you a couple of projects here, just to where to go from here, because making LED blink is not really really that exciting. So here is a little project I did quite some time ago. I had this earlier on with the 7-segment display. But what I can do is here, I have a strip board. So this is basically the next step where I can use a soldering iron to actually make permanent connections in my circuits. It's not just like a breadboard. If you have a breadboard, if you do something more complicated, it will look something like this here, which is difficult to look at. And if you have a cat, not good. Cats love to pull out these wires. But let me just show you what this one is here. So I have a battery, I can connect this. And when I fire this up, there's a button here on the side. When I push the button, it does a little animation, and it's basically electronic dice. So I wrote a little sketch that queries the button, and whenever I push the button, it just does like this animation. You can control each of those 7 segments individually. It creates a random number and then it flashes. This is like all written in a little bit of C code. It's not a lot of code. One little project that's maybe is fun, but let me show you something else. I also have the link to this in the slides. Let me show you another project that I did. And this crosses over into the area of data science. So here is another little project that I did. And you can see there are 3 LEDs. It's difficult to see here: blue, green, and red. On the top here, this thing here is a 3-axis accelerometer. That is the same device, the same sensor that you have in your smartphones that can detect orientation change. So when you turn your phone on the side, this is done by an accelerometer. What I've done, I have written an application, an Android application that collects data, different human activity, standing, walking, jumping. And I trained a mini neural network with this training data. And I put this mini neural network on the Arduino here on this chip. And when I now simulate different motions, so the red LED lights up because I'm standing. So let me just slowly move it up and down. I'm basically simulating walking, and you can see now the red LED goes off. Now it's the green LED. Now I'm hopping, I'm simulating jumping up and down, and the neural network, it's kind of hard to do it with my hand here, but you can see that now the blue light shines up. And if I stop again, it goes from green down to red. So think about earthquake. Think about asking the geography department for some historical data of earthquakes, and you train this neural network to recognize an earthquake. And you have now a little appliance that can detect when things are shaking, and you can have a little warning when earthquake goes off. I mean, that is the power of the Arduino. The human mind is, your imagination is the limit, and that is where I would encourage you to play with it. I'm really a big supporter and proponent of the Arduino. I mean, what I've shown you earlier with the button and the LED are Mickey Mouse examples, right? But I just want to give you an idea on what you can do from here on, and for SF Hacks, I would encourage just to look out for what different kinds of sensors there are. There are dozens and dozens of sensors, from irrigation systems to weather station to door openers. You can just do whatever you want. The mind is the limit, look through my slides. I have some more examples later on, and then hopefully it will give you some inspiration on what maybe you can do then during SF Hacks. Yeah, and with that, it's 6:15, but we also started late, so I don't feel really too bad about going overtime. But thanks for your attention, and yeah, I'm happy to do a follow-up or a repeat in front of a live audience then on campus if you want to do that again in spring 22.
100%, we definitely will. Thank you so much, Dr. Puder. I really like the neural network thing that you had. That was pretty cool that it changed colors.
Yeah, thank you so much.
I have the whole code is up on GitHub. So the Android code that collects the training data. So I was at one point walking up and down as to collect the training data, and the code to train the neural network, it's all on GitHub. Plus then the sketch and the wiring for what I've just shown you here. So if you want to replicate this, is all on GitHub.
Okay, thank you so much.
Thank you, Dr. Puder.
Super cool.
Thank you so much.
Thank you.
Okay, guys, then
Okay, bye.
We end the meeting. I just wanted to give a little bit more info about SF Hacks. We will be having our last workshop of the semester on December 1st, and that will be our game development workshop. And then if you want to keep in touch with us through social media, we have the QR codes right on the slide. And thank you so much.